Great. So why don't we go ahead and get started? I'm Jen Rexford, and Nate Foster and I co-lead the Network Programming Initiative, and we're really delighted to have you all here for the monthly NPI webinar. And today we're going to have Adam Wolnikowski from Yale, who's going to talk about his work on Zerializer. And he just graduated from Yale earlier this year and is working at Humatics now. And thanks so much for coming to tell us about your work. I'll let you take it away.
Of course, thank you. Yeah, it's exciting. I mean, clearly I'm freshly minted undergrad, so it's kind of the first opportunity to give a talk. So thanks for having me. I'm excited. I will share my screen. Do you see the taskbar down there?
We just see your screens and we see your cursor.
Okay, perfect. I guess.
Yep, looks good.
Sweet. Yeah, so this is Zerializer, an effort towards zero-copy serialization. We published this work at AutoS just recently in June, and it was a collaboration with some colleagues at Stanford and Intel. So I'll begin just with a kind of a brief overview of network I/O. For a while in the field, of course, zero-copy I/O has been a goal. Unfortunately, fortunately for some applications, but unfortunately for the networking people, distributed applications are on the rise, and there's a trend towards more distributed systems, more microservices, and just generally distributing large services as much as possible. And these services rely very heavily on application level serialization. The reason that's unfortunate for the networking side of things is that application level serialization just entirely obviates all the benefits that we put into zero-copy I/O. To illustrate this, for instance, we can see the path that a serialized object takes in transmission from the application being serialized. So you begin first just with the in-memory RPC object unencoded. It goes through the application and through the RPC library, undergoes the data transformation into the encoded RPC format. Then it needs to be transferred again into the kernel socket buffers, and finally transmitted out through the NIC queues. So it's a relatively long and rigorous process. That's a good number more copies than zero copy. And of course, the goal would be to just perform serialization directly between the unencoded memory representation and the NIC queues between A and D. So just a primer on serialization for those who might not be incredibly familiar with it. It's really just a translation of data structure in memory to a format for storage and transmission. The data might be nested, it might contain pointers to different memory locations and be non-contiguous. The serialization takes care of that. It also takes care of any architecture dependent discrepancies of the data. So, handles byte order, memory layout, everything so that it can be simply transferred from one platform, one environment to another. There is a bit of a distinction here as I'm talking about serialization. I kind of break it down into two parts. One part is the data transformation or the encoding, which is the physical transformation of the data itself, which, for example, protobuf has a representation of integers that is a bit different than your normal int32. And so there's some computation that has to happen where that's the bits are rearranged and that's manually transformed. But then we also think about serialization, including all of the memory operations that have to occur for it to, whatever the object is, to actually be transmitted out of the wire. So under broad strokes, I'm referring to serialization as the whole process, and then I'll call the actual encoding or data transformation. So it turns out that serialization is in fact a major bottleneck. Google reports that serialization alone is responsible for 5 to 7% of all of their CPU cycles in their data centers. And then if you include the kind of associated RPC costs, you get to 12% of all the cycles. So, I mean, this really is a sizable chunk of data center performance. Altogether, it's not due just to the inefficiency of serialization as it's currently implemented, but there's also the fact that, as I mentioned earlier, we're distributing applications more heavily, we're breaking things down into microservices, and so we're just ending up with an incredibly high frequency of invocation of the serialization routines, and with a typical service involving hundreds to thousands of RPCs. Additionally, as network speeds reach or exceed 100 gigabits per second, we end up with finer-grained operations that complete in microseconds. The serialization just becomes a increasing major source of overhead. So with this in mind, we believe that the necessary approach is to offload serialization to the NIC. And next, I'll kind of discuss why we think that is an appropriate response. So serialization, as I mentioned earlier, it's a combination of memory copy and compute. In terms of memory, there are a couple issues. Encoded data from the network obviously results in a cold cache. The CPU has to perform the encoding and decoding, so you travel the memory hierarchy back and forth. And finally, once the encoding's finished, you have to actually write back the native application formatted data back to memory before the application then goes and grabs it again. So you're just traversing the memory hierarchy more than you'd like to. And this does dominate the bottleneck of serialization. But importantly, obviously, there still is the pesky little encoding that you have to do. It's not incredibly expensive, but it prevents you from being able to just use DMA for the whole process. I would like to mention that measuring this this breakdown is very challenging. And I mean, these are the figures we found when we presented this work at HotOS. Another group out of Stanford, the paper in question was Breakfast of Champions, also with like a zero copy IO subtitle. They came to very different conclusions. They found that encoding was more like a third to almost a half of the overhead. And so it's highly dependent on, of course, the message type of what you're encoding. This is simply just like an integer triple, which we saw that typically does come up often in many applications. But they looked at other message types. There's also an issue of finding representative data, not just the actual type of the data, but the magnitude and the values. Obviously, that can vary incredibly between application to application. And if your application is serializing such values that protobuf's variable length integer encoding benefits greatly from, then you're probably going to focus more on the overhead than if you're using the entire width of the integer with every message. And so it really is heavily application and data dependent, and it's kind of hard to pin down exact numbers. And these numbers do really drive kind of the philosophy of the rest of the work. So I mean, it's a pretty important point, and I think that working on better profiling of this could lead to some interesting design choices. But going with the numbers that we have, the first question that you might ask is, why not just make software changes? Avoid unnecessary offload, unnecessary hardware acceleration, and just optimizing the software. So, I mean, within serialization, there are different trade-offs you can make. A variety of libraries, for instance, flat buffers versus protobuf, they can trade off human readability versus space efficiency. They can trade off performance versus expressiveness. Flat buffers is a lot less expressive, but it is more efficient than protobuf, for instance. So like there are trade-offs and there's optimization to be done in the software domain. That is true. But ultimately, you still do have to traverse the entire memory hierarchy, and you have the extra memory copy. So we feel that that's kind of the base issue with this, and that software simply can't address that fundamental issue. So next, you might say, why not just use another CPU? You can exploit some parallelism and optimize there, but ultimately, the CPUs are not optimized for bit level encoding. We observed 25 instructions per byte just for the protobuf varint, like variable width integer encoding that I've been talking about, and this blows up to thousands of instructions per message. Additionally, data encodings tend to be sequential, and this generates dependency chains with conditional branches that are challenging to execute efficiently on CPUs. And even if you do come up with some scheme to do this nicely in parallel, where you serialize, deserialize on one core and run the application on another, you still are seeing the fundamental problem of extra memory copies. You're not getting the zero copy item. Similarly, you could add an accelerator. This could solve the problems of CPUs not being well suited for the bit level encoding and the dependency chains. And it addresses the computational needs there, but it still does not address that fundamental extra memory copy. You're still traveling to both the accelerator and the CPU domain. So with all this in mind, we conclude that the transformation must be on the DMA path. Even with DMA, any accelerator-driven CPU or accelerator approach undoes all of the engineering meant to achieve zero-copy network interfaces. As I've mentioned before, repeatedly, the serialized data travels up the memory hierarchy and it travels back down in each of these schemes. This also, it uses the cache inefficiently, since the encoded data is only touched once before it's decoded. And ultimately, a true zero copy approach requires the NIC to be able to decode the messages before a DMA transfer into main memory or the last level cache. We also believe this is feasible, mainly thanks to, sorry? We believe. Okay, so we believe this is feasible thanks to much renewed interest in transformer protocol offload, and ultimately serialization deserialization is much simpler and less expensive than offloading a transfer protocol. So it could share certain elements, and ultimately, if we're thinking that transport protocol offload is feasible, we believe certainly that this would be as well. Additionally, the very small bandwidth delay product of the modern data center really means that NICs have more than enough memory to do this. So I'll go into our proposed design next.
So Adam, one question in the chat. I don't know if you want to take questions as you go along,
Sure.
but one question in the chat is, when you say extra data copy, do you mean the data copy from the kernel to the application, or due to serialization itself?
Due to serialization, because you have a copy of the data in encoded form and decoded form, right? And both of these are traveling the full memory hierarchy instead of kind of what I'm about to show, where you have depending on whether you're going in or out, but you have one form and the transformation happens in the NIC, and then you don't have to have both forms travel the entire memory hierarchy.
Okay, awesome.
Yeah, and sorry, I'm not looking at the chat, so if anything.
No, of course, if something comes up, I'll try to raise. Marvelous, thank you.
Yeah, thank you. Right, so at a high level, kind of addressing that question, we integrate a serialization deserialization pipeline straight into the NIC. The interface that exposes to software is very similar to that of modern DMA NICs. And essentially, RPC messages are automatically serialized and deserialized as they come in and out of the NIC. So, and as they're DMA'd to from memory. So from the application's perspective, it really seems as if data is just appearing deserialized and leaving in a native format. The application doesn't have to worry about the serialization whatsoever. So to initialize the serializer for this process, there's a couple of simple steps that need to occur. First, you have to allocate TX or transmit and receive descriptor rings and transmit and receive arenas and register them with the Zerializer from memory. These arenas store the RPC message to objects, so the host has to populate the IOTLB with the necessary virtual address to physical address translations. And then finally, a domain-specific language, such as protobuf, is used to define a application message format, which is then compiled into a message schema loaded into Zerializer. So the Zerializer itself stores the schema of the messages that it's expecting. So with that initialization completed, The serialization process begins with an application allocating and initializing an RPC message object in the transmit arena. It creates and adds a descriptor to the transmit descriptor ring, and it notifies the serializer with an MMIO write. Then the reader module fetches each field of the message from memory, and the encoder module independently transforms the fields in parallel, leveraging any knowledge it can from the message schema to do this as efficiently as possible. Finally, we have a merger module that accumulates the transformed fields and combines them into one final serialized message that is then transmitted out onto the wire through the NIC. As you can see here, this does rely on transport protocol offload. I guess I kind of didn't make that point incredibly clear earlier. We believe it's feasible because transport protocol offload seems to be feasible, and we also rely on transport protocol offload. So given that, we can implement the zero-copy serialization. The inverse process, deserialization, is similar, but there are some important differences. So begin with the NIC transport layer reassembles the packets into their serialized formats. The parser module identifies the message type and informs the allocator. This is kind of the big important difference here is that on this end, on deserialization, Zerializer is actually doing all the memory management. On serialization, you have the application manage memory and transmit that to the Zerializer with MMIO writes. But here, of course, the Zerializer is ingesting the new messages and has to do the memory manage itself. So so the parser informs the allocator, which then allocates an object in the receive arena according to the schema and the message format. Similarly to the encoder, the decoder then uses the message schema that's stored to transform message fields in parallel, and again do this as efficiently as possible with the schema in mind. And finally, this is loaded into the writer module, which uses the pre-allocated message object from the receive arena to populate with the deserialized data. Finally, the application either can pull the descriptor rings, or you can configure the Zerializer to generate an interrupt to the application as data is submitted. Yeah, maybe any questions on the design? If not, I'll. Oh, sure.
Sorry. So what kind of application you are assuming to use? Since now I can only see you are doing zero-copy serialization, but eventually you want to achieve zero-copy as well, right? So are you assuming use like a kind of an XTB application? So application can directly push the packet descriptor to the ring buffer?
Yes, that is kind of the assumption in this case.
Okay.
That could honestly be abstracted away and layered somehow from higher level applications, but that's kind of what we're assuming.
I see. Cool.
Yeah.
Thank you.
Yeah, so I'll continue on to kind of the evaluation we've done so far. We did it's pretty preliminary work so far, but so just to get a sense of, in general, the benefits of what zero-copy serialization could provide, we began with a test set up with the Intel's Deep Insight telemetry tool, configured in two versions. So one was configured just in its standard setup with Apache Thrift serialization and Kafka publishing, doing the entire process end to end with the serialization and deserialization. And the other setup was with a quote unquote null publisher, just counting messages. And this publisher, in essence, it kind of simulates what from the application's perspective, how zero-copy serialization would appear, given that just messages arrive deserialized and are transmitted in a native format. Obviously, it's a dummy publisher, so they're not actually being transmitted, but just to get a sense of kind of the order of magnitude of performance that we could expect from zero-copy serialization. So this test put us, a pretty exciting three times increase in throughput. and as I say, this is kind of a dummy test, but it is enticing figure. We also kind of mentioned that if we achieve zero copy serialization, that also enables the possibility of total RPC offload. It's a bit further out of the scope of this work, but it's an exciting potential benefit, just entirely offloading RPC to the NIC.
Hi, I have a quick question about that.
Yeah, sure.
So it's reports, are you saying that you're deserializing the INT reports that are coming straight off the wire, like from the network, or is there some other higher level API, like say Deep Insight sends alerts to clients or something? Like, what are the messages here?
Yeah. I didn't directly did. Yeah.
Maybe it'll help if I give my understanding of Deep Insight. My understanding of Deep
Right.
Insight is that the network generates INT reports, attaches those headers to packets. Those packets get sent to Deep Insight. Deep Insight consumes those and then makes a GUI for the operator to look at. Is it on the reports that are coming from the network, or is there another RPC interface happening here?
So it's on the reports.
Okay.
We're essentially publishing like dummy reports to simulate them having already been deserialized.
Okay, cool.
Yeah, it's a bit generous, but we believe that is representative kind of what the application would see in a zero copy situation. That makes sense.
Yes.
Yeah. Okay. Great. And then we did do some kind of proof of concept implementation, just with like a simple Verilog module. We implemented essentially just the protobuf variable with integer encoding to get a sense of what the kind of breaking down the serialization, not looking at the memory benefits, but just to kind of examine how difficult the encoding would be and how resource intensive. We just implemented it in Verilog. We were able to achieve relatively tiny LUT and register utilization figures, compared relative to an entire IceNIC or a Rocket Core, just for perspective. But really, it should provide, should be able to provide with full implementation, low cost and line rate performance. The only kind of memory overhead to this design would really be the schema metadata that would have to be stored. But that, it's a schema, it shouldn't be particularly memory intensive. And it's certainly not more expensive than like a transport protocol in terms of NIC memory, and especially it could share the same memory in a NIC that was configured to do both the transport offload and the serialization offload. This is the throughput that we observed on FPGA running this module, and now we're building out a lot more implementation to truly evaluate this approach versus a coprocessor approach. Wanting to we're implementing it in a attached to an IceNIC, and want to simulate this approach fully end-to-end serializing mostly just integer messages. We want to expand it to more, and compare that versus the approach with an entire coprocessor implemented in a similar fashion. So that's kind of where we're heading with this, and we'd love to see from that experiment kind of get some more concrete evaluation. So yeah, thank you. That's I guess came up a little short on time, but that's what I got, and I'd appreciate any questions.
Awesome, thank you. Do folks have questions?
So I have a question. Hi, thanks for the great talk. So I have one question about the network stack install, like you implement on the NIC. So currently, what's the protocol, like TCP, UDP, or currently using?
In the various kind of setups, I suppose we haven't actually implemented the entire setup with the NIC. with the FPGA experiment, I mean, that's, kind of the transport protocol doesn't come into the picture yet. I believe with Deep Insight, it's TCP, and similarly with the further implementation we're doing with the expanded implementation in the IceNIC, I think that's also TCP.
Yeah, so I'm thinking then perhaps because if you're using TCP, then perhaps the TCP engine also becomes another bottleneck. So I'm thinking, what is like, do you think what's going to be the challenge when dumping the TCP stack on the NIC and all of the memory bottlenecks in the NIC? Like, do you think the performance is going to, like, is there going to be new challenges when combining all of them together?
Right. I mean, I'll admit I'm not incredibly knowledgeable about transport protocol offload, but I mean, I'd assume that that is much more memory intensive, I think, than the SerDes offload. So certainly, just the memory constraints would probably be primary. In terms of any like confounding difficulties between transport and SerDes, I don't know that one would like necessarily make the give rise to challenges in the other, just from my knowledge, but I'm sure as it gets implemented, there's going to be stuff done.
Okay, cool.
Yeah.
Thank you. Yeah.
Actually, I have a follow-up to that question, which is there's a work from Jen's lab or from Amina Tamasbi Arashlu called Tonic, which is on offloading TCP and similar protocols to an FPGA. Are you aware of that work?
I am not. I'd love to.
Maybe useful to look at. So
yeah, definitely. I mean, yeah, because we've been looking at various methods of actually implementing this. One thought we had was to not necessarily even go the FPGA route and actually use try to implement it in P4. That was met with like mixed success. It's a bit difficult with like recursive messages to, if you have to expand a message in some way to get it back to the front of the pipeline. That's kind of the bottleneck we ran into there. So I mean, ultimately, yeah, this would probably end up on an FPGA or just in silicon. So yeah, I'll definitely take a look at that.
Well, my understanding is with current with current NICs and smart NICs and stuff, like, even if you write something on P4 for it, it still ends up in an FPGA at the end, right? I don't know if dedicated P4 chips on.
No, certainly. I just mean, instead of entirely in RTL, like if we can package this some way to play nice with like a smart NIC.
Yeah, I guess P4 is a little bit easier. Yeah.
Yeah.
Great. Other questions? Great, thanks so much. And we'll have another webinar next month where we're going to have talks from papers that will be appearing at SIGCOMM in August, but we'll send out information about that shortly. So thanks so much for joining and have a good rest of your day.
Yeah, thank you so much.
Adam. Appreciate it.